Okay, in this video, we want to talk about quantifiers and negations, which is what's missing so far from our logic is quantifiers. So first I need to give you a reason to understand why we need quantifiers. So the kind of statements we want to make in mathematics are the following things. Like we're going to say things like, for all n in the natural numbers, n is even. In fact, we've said stuff like that before, and then you could say something like, there exists some n in the natural number such that n is even, right? We've made statements like this. Now, the first one we wouldn't make exactly because that's false, but we've said things like that. And the second one is true, right? But the point is that we make statements in mathematics like, for all something such and such is true, and we say things like, there exists something such and such that this is true, right? So these are what's called quantifiers. And so in notation, we're going to have two different things here. We'll have the universal quantifier, which is denoted by this upside down A, capital A, which means for all. And we'll have what's called the existential quantifier, which is given by this backwards E, and that means there exists. Okay, so we're going to formalize this in this logic notation by using these symbols for all and for there exists, and that's going to allow us to write everything symbolically. And okay, so how do we, let's just start by looking at some examples of how we can work with these symbols. And this will also be a very helpful shorthand for us. So that will also be a benefit. Okay, so for instance, we could say there exists an n in the natural numbers such that square root of n is in the natural numbers. We could say for all n in the natural numbers, square root of n is in the real numbers. We could say that there exists an n in the natural numbers so that, sorry, we can say that it's not the case that there exists a natural like this, where square root of n is equal to n plus 1. We could say that there exists a natural number such that n is equal to minus n. We could say that for all n in the natural numbers, square root of n is in the natural numbers. And we could say that it is not the case that there exists an m in the natural numbers where square root of n is equal to n plus 2. You'll notice in the structure of these things that before the quantifier, if I take away the quantifier, then you get an open sentence. But since I'm quantifying things, it's no longer an open sentence because I can decide the truth or falsity of whether there exists something, whether for all something it's, something is true. So now I want to decide whether these things are true or false, right? So let's see, the first one, does there exist an n such that square root of n is a natural number? Well, 4, right? The square root of 4 is 2, so that's still a natural number. So that's true. The second one says for all natural numbers, it has to be the case that the square root of it is a real number. Depending on how much you know about this, you might not know this for sure, but that's actually true. Every square root of natural number is a real number. You're never going to get a complex number, for instance, by taking the square root of a positive natural number. Okay, now we're saying it's not the case that there exists a natural number where the square root of n is equal to n plus 1. That one you might have to think about for a little while, but that actually winds up being true. There's no such natural number where that is the case. Okay, So next one, there exists a natural number such that n is equal to minus n. Well, that's going to be false. I mean, notice that would be true if n was 0, but we don't allow 0 to be a natural number. So I guess it depends on your conventions of natural numbers. But for us, 0 is not a natural number. So there's no natural number so that n is equal to minus n. Okay, the next one. For all natural numbers, square root of n is a natural number. Now this is false because now it's saying for all natural numbers. So sure, the square root of 4 is a natural number, but the square root of 2 is not, right? So it's not true that for all natural numbers, the square root of that thing is a natural number. And the last one says it is not the case that there exists a number n, a natural number, so that the square root of n is equal to n plus 2. So this one's a little bit tricky. So it is not the case that there exists a natural number where the square root of n is equal to n plus 2. So what do we think? Well, I think that's actually true, right? Because if you take the square root of n, you're going to make the number a lot smaller, and n plus 2 is going to make it bigger. And so there shouldn't be any natural numbers with that case. So this is actually true. Okay, good. So now I want to look at some more examples of these kinds of quantified statements and try to figure out if they're true or false. But now I'm going to change it up slightly what they look like. So now we're going to do sort of two quantifiers in a row. So let's see some examples. So now we see for all x in the real numbers, there exists a y in the real numbers such that x squared is equal to y. Okay, the next one. There exists an x in the real numbers such that for all y in the real numbers, x squared is equal to y. Then the next one, for all y in the real numbers, there exists an x in the real numbers such that x squared is equal to y. And the last one is that there exists a y in the real numbers such that for all x in the real numbers, x squared is equal to y. Now you could ask the question here, how do I decide where to put the such that, right? It's actually, you don't do this when you do like completely formal logic, but in mathematics we do. We just put the such that where it makes sense when you say it out loud, but that means it's after the existential quantifier oftentimes. Okay, so now I want to decide whether these are true or false. And, it gets a little trickier when you start doubling up the quantifiers. And what makes mathematics quite difficult at times is because sometimes you'll double up quantifiers, sometimes triple up, quadruple quantifiers. The statements can get quite complicated as far as how many quantifiers there are and how the quantifiers relate to each other. Okay, so this says, for every real number x, there exists a y such that x squared is equal to y. Okay, well, that's equivalent to saying that basically there's always a square root, right? Because you can rewrite this, though this isn't quite the same thing. You can rewrite this as saying that there is some y that's equal to plus or, x is equal to plus or minus square root of y. So it's like saying that there's a square root. And so that is true, right? There's always a square root in the, no, sorry, I'm saying this wrong, right? So let's see. For any x, there exists a y such that when I square x, I get y. Yeah, so this makes sense because when you square x, you'll always get a positive number, and it'll have to be a real number, so there it will be equal to some real number y. So that's true. Okay, the next one. There exists an x such that for all y, x squared is equal to y. Now this is false, right? Because you can't pick an x, so you're going to when you say there exists an x, it's like you're picking one. You can't pick an x so that for any y, it's always x squared is always equal to y, because, for instance, if x was 2, then you're saying 2 squared, which is 4, is equal to every real number y. That can't possibly be the case. Okay, the next one. So for all real numbers y, there exists an x such that x squared equals y. Now this is also false, because what if you let y be negative, right? So now you're saying for all real numbers, so that means it has to be true no matter what real number I pick. But if y is equal to -1, then I can't pick any x and square it and get a negative number. So that's false. Okay, now the last one, there exists a y, a real number, such that for all x, x squared is equal to y. So now when you say there exists a y, you can think about fixing one so that no matter what x you pick, when you square it, it's equal to y. But again, that can't be the case. You can't fix an x and have it be equal to the square of every, so you can't fix a y and have it be equal to the square of every x. That just doesn't make sense. Okay, so that's our beginning of working with quantifiers and deciding the truth and falsity of statements involving quantifiers. So now we want to work with negating quantifiers, right? So that's the next thing we want to play around with. So here we're going to make a note. So when negating statements involving and or there exists and for all, we use the following rules. These are going to be like shorthand rules here. So the not of and is an or. We saw that with De Morgan's law. The not of an or is an and the not of for all is there exists, and the not of there exists is a for all. Now it's a little bit funny that I'm using equal signs here, so that's why I'm doing this as like a note. I really shouldn't be using equal signs, so this is me just communicating notation to you more than it is like some actual equality and as some like mathematical equation. So just to be clear, but that's telling you how the notation works for negations. So now let's play with this a bit and see how to negate things. So for example, let's say that R is the statement that for every real number X, there is some real number Y such that Y cubed is equal to X. Okay, so first of all, I've written R, the statement, in words, and now I want to do it using quantifiers. So R is equivalent to saying for all X in the real numbers, there exists a Y in the real numbers such that Y cubed equals X. Okay, so now I want to know what is the statement not R. Okay, so first of all, I can just put a not outside, right? A lot of times we abbreviate such that like this. So let's do that. Okay, but now I want to push the not through. So I want to say that not R is the same thing as, so when I push the not through, remember not for all means there exists. So there exists an X in the real numbers. Not there exists means for all. No, okay, sorry. Normally we put the such that in a different place now. So such that for all Y in the real numbers, and now we say we not the equals, so that becomes not equals. And now let's just rewrite this in plain language. So it says that there exists a real number x such that for all real numbers y, we find that y cubed is not equal to x. Okay, so translating back and forth between a sentence written completely in words to a sentence using quantifiers, then negating the sentence using quantifiers, and then translating back into a sentence only using words is important practice. So that's why I'm doing this kind of thing, and you'll do this on your homework. And let's just do another example similarly where we negate things. So now we want to start with the expression that for all x in the rationals, there exists a y in the rationals such that x does not equal minus y. So then if I negate that, well, then the negation is logically equivalent, so I can use this if and only if, to the following statement, which is that there exists an x because the not hits the for all and becomes there exists. Then when it hits this there exists, I get a for all. Notice it changes the quantifier, but it doesn't change where the x or the y lives. So you don't say there exists an x not in the rationals. It doesn't not the in part of the expression. Such that x does not equal minus y is what it's equivalent to. Okay, and if I do one more example for now, here, let's say the starting sentence, the statement is for all x in the real numbers, there exists a y in the natural numbers such that x to the power y is greater than or equal to 0. Then I want to negate that. And when I send the not through, this will be logically equivalent to the not of the for all becomes there exists. The not of there exists becomes for all. And the next part, when I negate the inequality, the strict or the greater than or equal to becomes a strict less than. So then such that x to the y is strictly less than 0. Okay, good. So that's our first look at the relationship between knots and ands and ors, but mostly knots and existential and universal quantifiers. And we'll keep playing with this as we progress through the class.